Hello and welcome to this lecture. In this lecture, we're going to study more about complex numbers. In particular, we'll introduce the complex plane very quickly, and then we'll move on to this important and interesting notion of angles. Okay, how to measure angles in radians? What is the connection between angles in the unit circle? How are the sinusoidal functions? How do they come about? All of that also will be part of this week's lectures. So. So let's get to studying the complex plane, unit circle and angles in radians. Okay. The complex plane is sort of an obvious thing once you have complex numbers, right? So all our complex numbers z have two real numbers in them, x plus yi. So it's very, very natural that you want to think of representing x plus yi on the complex plane. Okay, a real number we represent on the real line because there's only one number here, positive, negative, origin, all of that we do. Likewise, now you can represent a complex number on the complex plane. So this is a complex plane. There is a real axis, there is an imaginary axis. The point z equals x plus yi is the point x comma y. Okay. At some level, this is just like the 2D plane. Okay, nothing different from it, except that we are going to think of x comma y as the complex number x plus yi. So there's one subtlety there. So there are some connections because of it. Okay, otherwise it is exactly like a 2D plane. So for instance, the point x on the real axis, point y on the real imaginary axis, these two things connect to give you z equals at the intersection of those two you get z equals x plus yi. So notice usually we say x axis for this axis and y axis for this axis, right? Because it's complex, you say it's the real axis, imaginary axis. So any real part is sort of here, imaginary numbers are sort of here. To give you some example, okay, one more thing. So because this mod z is square root of x squared plus y squared, you see that mod z on the complex plane is actually the length of this line. Okay, so this is an interesting observation. And in fact, the conjugate is this other point here, x minus iy, right? X plus yi is z, it's a reflection about the x-axis is the conjugate z bar. Okay, so that's a nice thing to see as well. So mod z and z bar can be associated with z. Very naturally, you get a visual pictorial representation of these things. A few more examples. The numbers on the y-axis or the imaginary axis are called purely imaginary. There's nothing real about them because they have ai, numbers like ai, bi, whatever. I mean, any 2i, pi, any number you take here on the imaginary axis, that's going to be purely imaginary. Likewise, any number on the real axis is purely real or real. Okay, there's no imaginary part to it. So of course, most of the numbers are going to be like this, x plus yi. They'll have a real part and they'll have an imaginary part as well. Both are non-zero. Okay, more on here. So in this, for the real part, imaginary part, real numbers, real imaginary part is 0. For the purely imaginary numbers, the real part is 0. Okay, so this is a complex plane. It's very simple at some level, but nevertheless, it gives you a nice pictorial representation. Sometimes if you're confused, you can draw the picture and get some more clarity. Okay, so that's about the complex plane. Okay, so one can visualize operations just like vector operations. You can visualize operations in the complex plane. You have a plus bi and c plus di. You want to add them. There is this parallelogram law. You can see a plus c plus b plus di will be like completing this parallelogram. Is a very standard rule in the vector addition framework. So you see that the addition a plus c plus b plus d is like completing this parallelogram. That's one way to visualize. You can also visualize multiplication by a real number very easily. You take a plus bi, you multiply by alpha. Let's say alpha is positive. Then alpha times a plus alpha b, a alpha is positive and maybe greater than 1, maybe something like 1.8 or something. Then you would get some point here. On the same line, you would get a point further apart. So visualizing addition, visualizing multiplication by a real number seem to be very, very easy. However, if you want to do complex multiplication, now that looks like a different operation, isn't it? So a plus bi into c plus di. How do I visualize that multiplication on the complex plane? It doesn't seem very obvious. It turns out the secret to understanding this is all about angles. You need to know about angles in the 2D plane, angles in the complex plane and all that. So we're going to study angles for a little while. It's important idea. It's a standard idea. All of us know about angles. Been doing protractor and constructions for a long time. But what is angles in radians? What has pi got to do anything with it? So all of these things we'll introduce really quickly and then go on to study more interesting things. Okay, so everything starts with the unit circle. So you should get a good handle of the unit circle. In the complex plane, the unit circle is the set of all points z which satisfy mod z equals 1. right? You see how there is one subtle change in thinking about the complex plane and not just the real numbers. The circle, unit circle in the 2D plane, standard real 2D plane will be x squared plus y squared equals 1. Okay. In the complex plane, we will simply say mod z equals 1. Both of these are exactly the same. I am not gaining or losing anything, but every number on this circle now, unit circle, I am going to think of as a complex number. So, for instance, the number here on the x-axis is just 1. On the negative x-axis, minus 1. On the positive y-axis, this number usually is 0, 1, right? But that is nothing but I, the complex number I. Likewise, on the negative y-axis, what you have here on the unit circle is the number minus I. Okay. So, you see this 1 I minus 1 minus I. They are the 4 points on the axis intersection of the unit circle in the complex plane. Okay. So, this is one nice thing to know. Much more important than anything else with respect to the unit circle is we are also trying to understand angles in radians. Here comes the definition. Okay. Before that, I am sorry, apologize. Let me just come back to the unit circle. If you take an arbitrary point x plus yi on the unit circle, okay, you can draw this triangle, this right angle triangle. Okay, this right angle triangle is very important to know. Okay, there is a right angle triangle here. The base or one length of the triangle, one side of the triangle is just x. The height or the other side of the triangle of the 90 degrees is y, and this is called hypotenuse, isn't it? This side opposite to the 90 degrees is called hypotenuse, and that is the length 1, right? This is unit circle. So, clearly you see x squared plus y squared equals 1. So, those are the kind of points that are here, mod z equals 1, right? So, all these points. Now, this this point can circle around, and these lines will always circle around, and you will get you will get different right angle triangles. Okay. So, this triangle of connected to a particular point on the unit circle is very important, and that will play a vital role in this angles in radians. Okay. So, let us without further ado see the definition of angles in radians. What is the definition of angle in radians? Okay. So, forget about this axis, forget about this unit circle, right? So, maybe I should do that here. Okay. So, let us forget about the angle in the unit circle. How do we think of angles? You have a point O, you have a line A, you have a line B. Okay. The angle is some sort of a measure of this, how much this A has to sort of rotate around till you get to B, right? That is the measure. So, how do we measure this angle? It turns out this is the way to measure the angle. You draw a circle of radius 1 around O. Okay. Around O you draw a unit circle. Okay. This is not a proper circle, but anyway you know what I mean. A circle of radius 1 around O, and then this will hit okay, so maybe I will call this A prime, B prime. Okay. This will hit OA prime at A. This circle will hit OB prime at B, right. So, this is a circle of radius 1 about the point O where this angle meets, right. So, on this unit circle there is this arc. Let me draw this arc in a red color. This arc, this arc which is on this unit circle. Okay. So, the length of this arc is a measure of angle, right. So, this is the crucial and simple idea behind how to measure angles, right. So, you are at OA prime and you want to figure out the angle for OB prime. What do you do? About O, you draw a unit circle and then see if I travel along the arc on the unit circle, how much length I will travel. I will make that the measure of the angle. Okay. This is a very natural way to define angles, and this is exactly the measure for angles in radians. Why unit circle? Why not any other circle? That is just a convention. Okay, you can take any other circle length, but unit circle is sort of like the most standard and simple thing you can take. Nothing will change if you take any other thing as the standard, but the standard length that is taken is for the unit circle. Okay, so that's the angles in radians definition for you. Okay, the same thing I have written here. Okay, you have the unit circle. So, you see the role played by the unit circle in angles. You have the unit circle and this angle that's made at O between A and B, and A and B I'm taking to be the points on the unit circle. The angle is nothing but the length of the arc of the unit circle from A to B, and that is the unit of radians in angle. Okay, so you can easily see how pi enters the picture, right? Supposing A were to be on the x-axis, supposing A were to be the x-axis and B were to be on the negative x-axis. Okay, what is the arc length from the positive x-axis along this semicircle to the negative x-axis. We have seen this before, right? Perimeter, semi-perimeter of the unit circle, right? So that's just pi, right? So this angle from here to here is the angle pi radians, okay, which we also call as 180 degrees. So you see how pi enters the picture. The pi enters the picture because the length of the arc of a circle we measure in terms of pi, right? If it goes all the way up to from here to here, it's pi. If you go from here to here, it will be pi by 2, right? The quarter circle, that will be pi by 2 and all that. So pi enters the picture very naturally in radians. It's very easy to remember, but of course we may remember the angles in degrees, right? So we'll remember 180 as this angle, 360 as the overall angle, 360 is 2 pi, 180 is pi, 90 is pi by 2 and all that. Okay, easy to remember these things if you remember the circle. So the circle is very, very fundamental to measuring angles. Okay, so let's see a few more illustrations. So here is an illustration of how this angle swept by a radial line, how you should picture angle as the one that is swept by a radial line. So for this purpose, we'll fix OA along the x-axis, okay, and then this OB is going to be rotated along the unit circle, and as you rotate, this angle BOA is going to be the arc length of AB along the unit circle. And I want to just illustrate that with a small little thing here, and you see as B rotates, my angle which I usually mark as theta here is actually, what is the measure of this theta? This theta is the arc length of A. If you start from A, you go all the way here up to here. So this angle will be above pi, right? Right, I hope you see that. So somewhere here, maybe I should move this slowly. Somewhere here, my arc length will become, I'm not able to exactly do it, but you see what I mean. Somewhere here, the arc length will become exactly pi by 2, right? So that's pi by 2. And as I move along, if I keep moving along, if I come somewhere exactly here, I will get pi. Okay, at this point, the arc length is pi. Okay, the angle becomes pi. And then I keep on moving. I will get 3 pi by 2. Okay, somewhere here I will get 3 pi by 2. And then I keep on moving. Exactly there, I will get 2 pi. Right, so this angle theta is 2 pi. Now this OB has come full complete circle, and you got 2 pi. Okay, so hopefully you see this. This is a nice sort of demonstration of how the arc length and the angles are defined. Okay, so most people don't say arc length and all that. They'll just say angle in radians, and hopefully that's clear to you. Okay, so that's an illustration for angle swept by a radial line. So this picture is very, very important to remember. Any angle that you think of, always we think of angles in triangles and all that, but angles in the circle, which is actually very easily defined, is very, very important to understand as well. Okay, some specific angles of interest. Okay, so we saw a lot of angles there. Some of them are very important. First is theta equals 0, right? That's just this angle. There's no angle at all. Theta equals 0. Next is theta equals pi, which is on this side, right? And now pi radians is 180 degrees. So this is a standard conversion. We will pretty much not use degrees. We will always say radians mostly. But you might want to remember this because quite often people use degrees also for angles. And then you have pi by 2. You have 3 pi by 2, right? So pi by 2, and then that another pi by 2, another pi by 2 is 3 pi by 2. Okay, and then this is pi by 4. What is pi by 4? That's an interesting thing, right? So exactly halfway between these two, I don't know if it's exactly halfway, maybe I have not drawn it properly, but this is supposed to be exactly halfway between pi by 2 and 0, right? So if you do that, if you bisect this angle, you're going to get pi by 4, right? So this arc length is pi by 4, this arc length is also supposed to be exactly pi by 4. Maybe it didn't come out very good, but anyway, you can see where it is. This is pi by 4, this is also pi by 4, okay? So likewise, you can also have, pi by 4, 3 pi by 4, okay, right? This is pi by 4, another pi by 4, another pi by 4, right? Bisect this angle, then you will get 3 pi by 4. And then you will have 4 pi by 4, which is pi, and then 5 pi by 4. Then you have 6 pi by 4, which is 3 pi by 2, and then 7 pi by 4, and then 8 pi by 4, which is 2 pi. So you can think of it as 0, pi by 2, pi, 3 pi by 2, 2 pi. Okay, increase in pi by 2, or you can also increase the angle in pi by 4. Okay, you go to pi by 4, then pi by 2, pi by 3 pi by 4, so on. You can keep repeating this. No, you can go to pi by 8, you can go to pi by 16 or pi by 7. You can do that any which way you like. So typically the thing to remember is, mostly angles in radians, are expressed as fractions of pi. You will say pi by 6, pi by 3, pi by 4. So, and you can see why. I mean, it's just very easy to visualize it on the unit circle and see how it goes. Okay. So, angles and unit circles are very, very important. Like I said, pi by 4 is a very important angle. Pi by 4, basically this point x equal to y, right. So, that is an important nice thing to see, and you will get a lot of very basic results from that. Okay. So, hopefully you get a sense of angles and how they behave. Let us see some properties. Okay. So, there are some conventions and properties here. First convention is positive, negative. When do we say angles are positive? When you sweep them with the radial line about the circle, when do you say angles are negative? This is again a convention. You can say it any which way you want, but the most popular convention is to say the angle swept from x-axis in an anti-clockwise direction is positive. If you go in the clockwise direction, you say it's negative. Okay, so it's just a convention, but that's that's how it's done. So, for instance, if you go back to this picture, so if you started from here, you swept positively, you got theta equals pi by 4. If you were to sweep negatively, this theta equals 7 pi by 4 will be called minus pi by 4. Okay. So, are both these things the same? It turns out they are the same. Okay, that's because there is a periodicity to these angles. Any angle theta, if you add or subtract 2 pi to it, or 2 pi or 4 pi or 6 pi or something, you get the same angle. Why? Because 2 pi is one full rotation. You are coming back to the same point. You have at any angle theta, and then you rotate by 2 pi this direction, you come back to the same angle, or you rotate by 2 pi in the other direction, you go back to the same angle, right. So, this 2 pi addition or subtraction has no change to the angle. So, if you have an angle theta, theta plus 2 pi, theta plus 4 pi, all of them are the same. Theta minus 2 pi, theta minus 4 pi are all of them same. So, if you go back here, you have pi by 4 minus 2 pi, okay, I am sorry, pi by 4, okay, pi by 4 is there, that is okay. So, on the other hand, if you come to this side, you have 7 pi by 4, right, okay, minus if I subtract 2 pi, right, 7 pi by 4 minus 2 pi, you will get minus pi by 4, okay. So, you can check that, maybe I will do that here just to show exactly what I am doing. So, this angle, which is minus pi by 4, is also the same as minus pi by 4 plus 2 pi, which is equal to 7 pi by 4, okay. So, the 7 pi by 4 angle and minus pi by 4 angle are one and the same thing, because they add up to 2 pi, right. When they add up to 2 pi, nothing really happens. So, this angle I can call as 7 pi by 4 or minus pi by 2. Likewise, 3 pi by 2 is also called minus pi by 2. In fact, pi and minus pi are the same angle, right. You go this way pi or this way minus pi, you get the same angle. Okay, so you have to be watching out for that. Pi and minus pi are the same angle. 7 pi by 4 in this way is the same as minus pi by 4 in this way. 3 pi by 2 in this direction, anti-clockwise direction, is the same as minus pi by 2 going in the clockwise direction. Likewise, so the same angle you can get there two ways. You can rotate anti-clockwise or clockwise. If you do anti-clockwise, you get positive. You get clockwise, we usually say it's negative. Okay, that's all. So that's about positive, negative angles and periodicity. Okay, so here is the slightly more interesting and useful thing about these angles. So we kept saying that the angle theta is the arc length of the unit circle, right, on the unit circle. So here is a picture where I have the white circle, which is the unit circle, okay, and then the green circle, which is a circle of radius r, okay. So you see here x squared plus y squared equals 1 and x squared plus y squared equal to r squared, circle of radius r. Then I consider a line y equals mx, okay. This is a straight line passing through the origin, right, we have seen this before. This is a straight line passing through the origin, y equals mx, and that line makes an angle theta with the x-axis, okay. What is this angle theta? This theta is the arc length on the unit circle, okay. This is theta, okay, whatever the theta may be, okay. So an interesting observation immediately is that this arc length can be written as an integral, okay. We know how to write arc length as integral, right. So this we have seen before. Let me just quickly remind you of how I got one point here. So if you have a unit circle and you consider a line y equals mx, right, this point here, okay, let us say is x naught y naught, that is the point where this straight line intersects the circle, this point satisfies two properties. Y naught equals mx naught because it's on the straight line, and x naught square plus y naught square equals 1 because it's on the circle also, right. So, this is how you find point of intersection between a circle and a line. Line is y equals mx. So, point of intersection is to satisfy both mx naught and this. So, x naught square plus m squared x naught squared equals 1. So, x naught equals 1 by root of 1 plus m squared. So, this point, right, this length is this guy x naught, okay, 1 by root of 1 plus m squared. So, if I want to find the arc length, let me draw a slightly bigger picture here just for convenience. So, I have the origin, I have this length, this arc length, this is 1 by root of 1 plus m squared, and this equation f of x equals square root of 1 minus x squared, right. So, that is the equation of this guy. How do I find the arc length from here to here? I have to integrate from 1 by root of 1 plus m squared to 1 square root of 1 plus f prime of x squared dx, right. So, this is the arc length. So, this is theta, isn't it? Theta should be equal to this. So, what is f prime? One by 2 root 1 minus x squared times minus 2x. This 2 and 2 will cancel. So, you just get this. So, if you plug that back in here, you will get that this expression becomes equal to 1 by root of 1 minus x squared. Okay. So, you see theta can be written as integral 1 by root 1 plus m squared to 1 of 1 by root of 1 minus x squared dx. Okay. So, this is a standard arc length. We saw application of integration in the previous one of the previous topics, how to find arc length, and that is what is going on here. Okay. So, the arc length theta I have written as integral 1 by root of 1 plus m squared to 1 by square root of 1 minus u square. Instead of x I have used u, and that is okay, it is a dummy variable of integration. Now, the interesting question is, what is the arc length of the radius r circle? Okay, by the same, between the same line, between the x axis and the same line y equals mx. The arc length along the unit circle we saw and we called it theta. That was this complicated expression. What is the arc length if you go to a circle of radius r? Okay. So, here also you can do the same computation. So, this point will be r by root of 1 by r squared, 1 plus m squared. So, you integrate from r by root of 1 plus m squared to r square root of 1 plus f prime of x squared. Now, this f of x will be root of r squared minus x squared, right. So, you substitute that here, you will get this integration. Okay. So, take this as an exercise, f of x is square root of r squared minus x squared. You do this simplification, you will get this. Now, you substitute u equals x by r. Okay. This is going to simplify to this beautifully simple expression theta times r. Okay. So, here is a powerful and simple rule, right. So, if you measure the angle on the unit circle as the length theta, the length on a radius r circle, the arc length on a radius arc circle is simply theta times r. Okay. So, this is what I meant by saying it does not matter what circle you take, you can keep it as arbitrary. We have taken theta to be the arc length on the unit circle. The arc length on any other circle is simply theta times r, and here is the sort of a proof for that using integration. Okay. So, this is a nice thing to remember. So, once you know the angle, you know the arc length for any radius, it is simply theta times r. Okay. Okay. So, a couple of problems. These are quite easy to do. I'll urge you to draw a picture. For instance, circular racing track. You've seen these racing tracks. If you have a racing track, there'll be an inner circle, and then there'll be the width of the track, and you have to assume sort of that the person is running in the middle of the track or maybe the edge of the track or something, and then you want it to be exactly 200 meters. So, you can fix what should be the radius of the inside line, outside line. Okay, I'll urge you to draw the picture, measure the distance carefully, and then you will get perimeter formula as 2 pi r. So, you know what the radius is. Okay. Now, what will happen is, if you might have seen this before, in the 200-meter race, everybody will not start in the same line, and they will all not end in the same line. Okay. The reason is, as the radius increases, the perimeter is also going up, right? So you have to start a little bit ahead, right? The people who are on the outer tracks will have to start a little bit ahead. So that's the question that's asked here. For a 200-meter race with the same finish line, you want the finish line to be the same, how should the 8 participants be placed at the start of the race? Okay, so this is an interesting calculation. You have to see how far ahead each person has to be, so that the total distance they come will be exactly 200 at the same finishing line. You assume the finishing line is the same as the one in the innermost circle. Okay, so that way you will do a simple calculation. It just involves, lap angles and arc length of different radii, and you can do that calculation very easily. Okay, that's the end of this lecture. Thank you very much.